So I will go with the obligatory. It's a great honor to give a talk here to honor the 50th year of discovery of quasars. And I want to thank Maarten Schmidt specifically for opening the field of study that occupies me for the last 20 years very passionately. I probably would have worked on boring stars otherwise, or something like that. And I want to thank George and everyone around who are struggling to get my my slides up here. So I can do some dancing and pantomime. That's very true, yes. Anyone has questions? Can you anticipate the end of my talk? Any psychics in the audience?
Sorry, it's got a bloody timer.
Okay, well, I can start a little bit historical overview because I will show you 2 slides. And that is, very soon after Maarten discovered the first quasar, people discovered that quasars have outflows. Now, seen in absorption lines. They are always blue shifted compared to the rest frame. And I think the first paper that I was able to trace back is Margaret Burbidge was the first author, Cyril Linz was second, and rounding up the usual suspect was Jeff Burbidge. And it was on 3C191. And they basically got everything correct there. They said this is a different absorption than AGN absorption, and it probably has to do with shells of gas coming out from the vicinity of the central source, which at that point people did not know what AGNs are. And if you can see on this
32 seconds.
Okay. You're going to give me the time for that, right? Good. Excellent. But anyway, people have done a lot of work on these. I want to mention specifically Ray Wyman, who did a lot of work on bulk QSOs and outflows in the 70s and 80s. And when I came up, it was mid-90s, where people were already looking to see whether they can understand the physics of the gas. People honed on the fact that it's probably being excellent. Very good. Thank you very much. And let's see. Now, how do I, this is what I do. Okay, good. So, what I'm going to tell you today, I changed the title just a little bit to be the most energetic outflows in the universe. And what I'm going to do, thanks to the very long list of collaborators I have here, and I want to mention specifically my former postdoc Benoit Bourget and my current graduate student Carter Chamberlain, is something very interesting. As I mentioned a minute ago, we have seen this type of objects for good 40 years. These are the bulk QSOs. They have narrow companions or brothers that do not have to be as wide, but these are always thought to be the big absorption lines that are blue shifted several thousand and maybe 10,000 kilometers a second from the systemic redshift, showing you a gas that is outflowing from the center source towards you. We have seen them for a long, long time, and I want to try to shift your view of them to what I'm currently holding, and that is the following. And this is basically the punchline of what I'll say. I will claim that the average luminous quasar have these type of outflows, subrelativistic outflows, on very large scales of about 1,000 parsecs on average, large mass flow rates, 100 solar masses per year, and kinetic luminosity that is sufficient for all the beautiful AGN feedback that Phil told us about yesterday. And all of these are kind of big claims, so let me try to walk you through a little bit. So this is the paper that I talked about, Burbidge, Linz, and Burbidge, and here they say that the clouds, the absorption can be interpreted either like the Bacol and Salpeter as being intergalactic material, or they might be due to absorption in clouds or shell of gas which form part of the QSO. And they even make a statement that in this object, it's obviously number 2, that the absorption features are explained by a shell of gas that is emanating from close to the source. And they did all of that with this spectrum. which really boggle my mind. How can you do anything like that? But, you know, the giants of the past, the giants of the past, brother. Okay. Fast forward a little bit. This is, you know, an object that we took. It's also a tribute to Alex Boxenberg, who took a spectrum of this object with IUE in the mid-'80s, and then it was a very impressive bulk USO, so we followed it up by 40 orbits of HST and produced some massive papers about 10, 12 years ago about that. But what I want to show you here is how do we go about from the phenomena to try and understand if it influenced the universe and does all this AGN feedback at all. The first thing to remember, the first key for the whole thing, is that about 20 to 40% of all quasars actually show these type of absorption outflows. So they are very common, and we normally associate the percentage not with that only 20% of quasar has outflows, but that every quasar has an outflow like that, and it's only covered 20% of the solid angle. So we assume that it's probably ubiquitous to all quasars, and we only see it in a percentage of the case due to orientation effect. Is it going to amount to much in the whole scheme of galaxy formation, mergers, all kind of stuff like that? This is an empirical question that can be answered if we can measure their mass flux and kinetic luminosity. And this is what we will try and do. So we go to Margaret Burbett's shell. Okay? Here is a shell of gas that comes out of the AGN. And what I need to know, it's very easy to calculate the speed, of course. The speed is very easy. And once we put it on this laptop, we have all kind of interesting music symbols too that are not in the original picture. Anyway, what we need to get, we'll get them plenty. We need to know the mass per unit area of the shell. In astronomical language, this will be the column density. It's easy to transfer to them. We need to know the radius of the shell, the distance of the wind from the central source, which will give us the total size of this shell. And it's probably not going to be a shell. It is going to be a portion of that, so we'll call it a fraction of the full 4 pi star radian. If we have that, then it's not very easy to calculate, and not very difficult to calculate, but the mass of that shell will be 4 pi r square times this expression. And m dot, because we only have a snapshot in time, what we'll do, we'll use the simplest prescription. We'll just divide the mass by the dynamical timescale. And for the kinetic luminosity, we'll multiply it by v squared. So what we get is this expression. These are the three observable that we really need. The proton mass was given to us a long time ago. And the 1.4 is to convert the number of protons to actual mass. Now, until about 5-6 years ago, the reason that we didn't really get too far in this business was because in the same objects, sometimes people had claimed that they detect 10 to the 20 column density to 10 to the 24, and that is in the same object. Even in astronomical accuracy, this is not good. The distances were also all over the place, from 0.01 parsecs to 10,000 parsecs. The only thing we knew quite well is the omega, which is about 0.2 from the argument I said before. So how do we go from the spectrum to getting the kinetic luminosity? This is a spectrograph of a mundane bulk USO. Those of you who have seen that have seen many of these. But this is also the spectrum of the world record in kinetic luminosity of any outflow that I know of in the universe. So it's a very kind of normal-looking object, and yet it is harbor a fantastically energetic outflow. And how do we go about that? So the first thing we need to know is to get the column densities from the trough that you see. People have done that for many years in ISM and IGM. We have some difficulties that no one encounters in other fields, and let me show you one very simple thing here. Okay? Here is data from X-Shooter on the VLT, phenomenal spectrograph. The bottom of the trough of carbon-4 here is a signal-to-noise of about 50 with resolution of 6,000. And the important thing to see is that the trough of carbon-4 is not black. It's not zero intensity. And if you will just take the apparent optical depth naively, you will get that the optical depth of the carbon-4 here is 3, just from changing the residual intensity into optical depth. What I'm going to show you that the actual optical depth of carbon-4 here is 1,000 times larger. There is a humongous amount of saturation here, and that affects all people that work on outflows. And this is why it is so essential to look very, very carefully and know what you can do and what you cannot. How did we get to this surprising conclusion? We have here phosphorus 5, as you can see here. We also have sulfur 4. Both of them are doublets, and we were able to get very accurate column densities and account for saturation. We found that the column density of sulfur 4 is 60 times that of phosphorus 5. Now, both of these, their ionization correction behave the same, so the ratio of the column density is independent, roughly, of the ionization parameter. And because of that, we can be quite confident that this will actually be the ratio of the atoms of all sulfur and phosphorus. Lo and behold, in solar metallicity, the ratio of sulfur per phosphor is also 60. Okay? Sulfur is 60 times more abundant than phosphorus, which means that this outflow has solar metallicity. Okay? The next thing we remember is that the ratio of carbon to phosphorus is 1,000 in metallicity, and therefore what we have is that because carbon is also have the same ionization correction, we're going to get that the carbon column density should be 1,000 times more than phosphorus 5, and then it's trivial to get the expected actual optical depth, and we get it to be 1,500 times larger than the optical depth of phosphorus 5. Phosphorus 5 is about 2, therefore carbon for the real optical depth is 3,000. So we are hiding 1,000 times more carbon-4 in that trough that is seen in the eye. Okay, so after this quick tutorial, and that was all published a year ago by us. The next thing we need to do is to measure the ionization parameter in the column density. A quick tutorial about that. How do we do it? We take the spectral energy distribution of a quasar, we shine it through a cloud using cloudy model, and we are trying to get the model that will accurately tell us, basically give us the column density that we measure after we so hard worked on measuring them correctly. And the gist of it is very simple. Here is column density measured in hydrogen. What we use is grid models where you have column density here, ionization parameter here. If you have a single measurement of H1 of neutral hydrogen, there is a locus of points here that you can either have a thin cloud, 10 to the 16.5 here, with low ionization parameter, or very thick cloud that is highly ionized. All of these will give you the same amount of neutral hydrogen. To know exactly where you are, you need another ion, and if you have the other ion, the crossing point is the physical solution. You can read off these grid models, the ionization parameter, and the column density. Okay, now we get to the crux, and that is determining R. Okay? This is where I think the main psychological issue for most people who are working in the field and observing it is. For decades, and especially for the 2 decades that I'm working on these, the main theoretical thoughts about these winds is that they have to be accretion disk winds coming close from the black hole. And it comes because we know that O-star winds, for example, or stellar winds, come from the surface of stars and give us these beautiful P Cygni profiles. We have beautiful theories to work with that. We also know that in cataclysmic variables, we assume that the accretion disk produces similar winds. So therefore, as you've seen in this conference already in several cartoons, and here is another one, everyone thinks that these are accretion disk winds. Okay? This is from Martin Elvis from 13 years ago, and I want to point out the important thing is the scale. The scale of the wind here, the wind is launched at about 10 to the 16 centimeters, which is less than 0.01 parsec. Okay? Now, this is what I call a classical theorist bias. We expect them to be there, we build our models, but it's not a question what theorists think or not. The question is what Mother Nature, where does it put the actual outflows? And for that, we need to empirically find that. So what do? We actually find empirical diagnostics for that. Brad mentioned yesterday the ionization parameter. I want to remind people the ionization parameter is a beautiful physical concept. It is the ratio of number density of ionizing photons to the number density of hydrogen in the plasma. It's exactly what it is, and it works very well. Now, pay attention that we have the number of ionizing photons per second divided by r squared and the density. So with the magic of algebra, I can actually solve for r. Now, this is Caltech, so your students really know this very well. So what I get is that I know Q because I know the luminosity of the quasar, the redshift and the flux. And if I will know the number density, since I already solved for the ionization parameter, I'm going to get R. So the thing that I need here is the number density in order to solve for that. The way we do that is by looking at absorption from excited states. This is, again, something that people know in stellar physics and other aspects of astrophysics. What we do is we take lines with the ratio of the excited state to the resonant state is prescribed by collisional excitation. And you can see that you have different sets of lines. Here is, for example, oxygen 4. If you have the excited state, the resonance, you can read the number density here. You already know the ionization parameter and Q. You can solve for R. And this is what we started doing about 4 or 5 years ago, and we continue doing that with a vengeance. And let's see what we actually get. So here is a spectrum that only its mother can love. Okay? This is an SDSS spectrum, already quite low flux. I sent my undergraduate student, Courtney Laughlin, to have a summer project 3 years ago. She came up with this object, and it's very ratty, noisy, but our software is good. And what I noticed instantly that we have these two lines. This is sulfur 4 resonance, and this is sulfur excited. And immediately I told her that this might be a very, very powerful outflow. I had immediately suggested that as an object to observe with VLT. In a year time, we got the observations, and we already know the drill, so this is what we did. By the way, the mention of Kramer here is that they are the first people that reported in outflow in NGC 4151 this absorption of sulfur 4. So we measure the column densities with our sophisticated methods, and we get the ionization parameter. We call these guys the rainbow plots because there are lots of different lines. The important thing is that phosphorus 5 here limits us very strongly. We get a high column density of above 10 to the 22. We also know the ionization parameter. Two very important things we need for the calculation of the mass and the kinetic luminosity. From sulfur 4 and sulfur 4 excited, we get the ratio, and we get the ratio gives us a number density of a little bit more than 10 to the 4. At that point, nature has spoken. We now know everything we need about the outflow. We know the size of it. We know the column density. It's simple algebra to go and calculate what's happening. So I'll show you the results that we have. The first important thing, and this is the dramatic difference between that and the picture of this wind that most people in this room have. The distance of the outflow from the central source is 300 parsecs. It is not 0.01 parsecs or 0.1 parsec, and that makes a huge difference. This is going to be a wind that is very powerful on galactic scale and can do a lot of things. It is not, we are not observing gas coming very close from the accretion disk. Many years ago, a million years ago, everything must have come from very close to the black hole, but when we actually observe these things, they are very far away, and this is a very important message I want you to take away from here. Once we establish that, we look at the actual kinetic luminosity. This wind has 10 to the 46 ergs per second kinetic luminosity, and it's the world record that we have so far. I remind you, this is 100 times more than the luminosity of the Milky Way galaxy. Okay? The wind in this object has what we have here. The percentage of the bolometric luminosity for this object is 5%. And here, again, talking to Phil and a lot of other theorists who do AGN feedback, The important thing is that you need to have about 1 to 5% of the Eddington luminosity of a quasar in the form of kinetic luminosity in order to do all this feedback. Now, here it is 5% of bolometric luminosity, but it's a very high luminosity object. So it's obviously very close to the Eddington, it emits very close to Eddington rate, so therefore the issue whether it's bolometric luminosity or Eddington luminosity is much smaller. This is very close to 5% of the Eddington luminosity of the object. And finally, we have 400 solar masses per year emanating in this outflow. All this was published in Bourgeois et al. 2013 in January. The other thing that will be interesting to the modeler theorists is that we have the single scattering momentum limit in these objects, m dot v divided by L over c, is larger than 20. So with a single scattering approximation, you cannot accelerate these winds. You need to have a more sophisticated mechanism to do that. Okay, not go for that. So this is an important part of the story. These are very big winds. And the second thing comes from HST data. In HST, what we have is we are covering a very important gap in our knowledge. What again? Yes, but the data will be from HST. This is just to show you what the issue is. The issue is that Chandra and XMM are telling us that these so-called warm absorbers have the high phase of the ionization in the gas. It dominates the actual outflow material. So in the UV, we only see a trace of the actual outflow. Most of the mass, most of the column density is in the X-rays. So they find 10 to 100 times more column density in the X-ray phase than in the UV phase. Now, the nice thing about HST and its powerful new spectrograph COS is the following. Up until COS, we were only able to see lines that are longwards of about 1,000 angstrom. Why? Because from the ground, we can't see much further than that. Lyman alpha becomes very, very opaque above redshift 3. And from space, STIS was not powerful enough to go beyond about redshift 0.1 for our purposes and give us high enough signal to noise. So we had to work with these lines, Lyman alpha, nitrogen 4, carbon 4, nitrogen 5, carbon 4. And so COS, if you look at outflows from about redshift 1, give you this plethora of phenomenal diagnostics. Every single observation of an outflow with high signal to noise in that region will transform the field. And this is why I'm begging the HST panels, not very successfully, to give us time in that. What you see here are two things. First, you have in blue, you're going to have the ions that are very highly ionized. You're going to have here the oxygen 6 that we see sometimes from the ground, but much more important, neon 8, magnesium 10, and even silicon 12. In red, you see all of the combinations of lines of resonance and excited states from the high ionization line that are so important to us, which are the majority, 90% of the outflows. So having told you how many lines we have here and how much diagnostics we have, the story is very simple. Here is a poster child that we just have published. These are troughs in neon 8. They are going to give us the same diagnostics for the warm absorber. Okay? Here you see the all-important oxygen 4 and oxygen 4 excited that is going to give us the number density of the wind and therefore its distance. So you've been through this movie with me before. We're going to get the oxygen 4 to give us a number density. We're going to get the rainbow plots trying to tell us where is the ionization solution. But we have a little obstacle. You can see here that the alpha really wants to be here, except oxygen 4 does not intersect there at all. So you get a committee compromise by chi-square that does not satisfy anyone. So the solution is here, but it's a terrible solution because it underestimate the oxygen 4 over oxygen 6 ratio by 50-fold. Okay? So what we have is we get actually 2 ionization phases in the outflow. And we have the high ionization phase here that indeed carries most of the mass, the low ionization phase from oxygen 4 that will give us the distance, and from that we can get the actual kinetic luminosity. We also figured out, we tested lots of different SEDs and lots of different metallicities. So we have all that, so what do we have? We have that the regular quasar will have a very powerful outflow in a galactic scale, in a kiloparsec scale coming from that. And we do have two phases with a filling factor of about 10 to the minus 4, 10 to the minus 5. I won't get into too much details here. The consequence for AGN feedback is enormous, because if you take over 10 to the 8 years the duty cycle of a quasar, then such an outflow, 10 to the 46 ergs per second, will give you 10 to the 62 ergs, which is more than enough to inflate the largest bubble that we see in the universe, McNamara et al., and people like that. These outflows are also much more useful for feedback in general because they have very wide opening angle. I won't go in chemical enrichment, which we can explain also. Phil talked about a little bit. For the dynamical modelers and a lot of people in the crowd, I want you to start thinking about the fact that when we see these outflows, they are very, very far away from the black hole. They probably have originated, the wind originated by a blast wave or anything else close to the black hole, but we don't see them there. So we need to think about model to create them in situ, 500,000 parsecs away from the black hole, and we are not seeing accretion disk wind in action. And so we start having work by that by different groups, like Claude-André Fouché-Gillot, for example. So the message I want to take home is most galaxies, in this view, had experienced a violent period of high energy, high speed outflow during their active quasar phase that influenced at least their 1 to 10 kiloparsecs. And this episode might have been the exact quasar mode feedback. And I'll leave you with this. Here is our 3 main results that we have published in the literature by now, all similar distance scales and similar energetics, and I thank you very much. Yeah, I would say that I'm not too worried about that. I'm aware of that and older work that said that phosphorus might be very overall abundant, but we have a whole string of elements that behave like that, and they behave very well by the expectation. Sometimes we see nickel, which is 10 times less than iron. So our picture is very consistent with the alphas being a little bit supersolar, about 4, phosphorus not behaving anything different, which is supported by other elements as well.
So 2 quick questions. One is, it's a completely different model, of course, that you're proposing, but I thought that there were time variations seen in the deep create galaxy, which would
yes.
rule kind of against such large distances, just the actual kinematic profile changes, not just the amplitude of the profile.
Let me.
Second thing is, what fraction of the gas is entrained? The residual high velocity suggests that not very much of it is entrained, and that it all originated from close to the sun.
Let me first answer the first point. I'm very well aware of the variability studies, and most of the variability studies we see in quasar are indeed troughs that are more or less stable, moving up and down, which can be explained by chain ionization flux. And that is because, unlike reverberation mappings of Brad, the reverberation mapping in absorption is a line of sight effect. So if the plasma is at high enough density, it reacts instantly or very, very fast, even if it sits 1,000 parsecs from the source. And with these kind of densities, 10 to the 4, 10 to the 5, the reaction time is measured in weeks. Very, very few times, and I would say about 1 to a few % of the cases, you actually see any shifts in the actual velocity. So the vast majority are not on that sort. Now, your second question, you'll have to repeat.
The entrained gas, the fact that the velocities are still high suggests that most of this gas was initially accelerated close to
Yes. Well, in that case, I think I believe in the physical picture that Tim Heckman is trying to advocate for more than 10 years, that the actual wind fluid is unseen. It's a very hot plasma that is moving these speeds, and everything else we see is entrainment of material that is being blown across the line of sight. And this is also in the model of colonel Dreyfus-Guyot, where basically what you see is ISM clouds being shredded, and on timescales of decades or hundreds of years, they can survive, and this is what you see as your troughs.
Oh, well, then you have very high ionization parameter material being accelerated, which becomes very difficult because the ions are completely...
Yes, what you allude to is that it's very probably the acceleration is not radiative in nature, or else when it did, it was so opaque that it really was working more like a bomb than anything else. I lost it.
And I was looking at that, and, well, you know, it could be detected, I guess. I mean, it seems like it could be an upper limit.
Do you know how to work this?
I don't know how you got disconnected from the display. Let's see.
And,
I'll try to do it without the slide.
You showed the bit, and maybe there could be a little bump there, or maybe there's not a bump there. So, suppose, for example, just take this, I'm trying to see which way this goes. Your entire result.
Mm-hmm.
Okay, I got it. You have to tell me which one you want.
Your entire result hinges on the fact that you claim there's a low density
Yes.
in this stuff.
Yes.
And so, can we trust this low density from that fine structure? One more, two more, next one.
That's
There
it.
is, right?
Okay.
There it is. So you
Mm-hmm.
got a little red thing that makes your fit a little better, I guess, than if the little red thing wasn't there. Okay, so I'm not sure about that, but here's the question. The question is, so can we believe these low densities? So I think what you're saying is, and if the density is lower, then the gas is even further.
Yes.
Okay, so as long as it's not high, we're okay.
Mm-hmm.
So if that turned out to be just an upper limit on the fine structure line, then that would mean that the density is even lower
Yeah.
than
Mm-hmm.
you said. And you were safe, because your basic conclusion will stand even stronger. Does that?
Definitely.
As long as the sulfur core is not too strong, indicating a very high electron density, in which case the other guys were right.
Yes, but let me support it on two or three little
So
things.
it's actually the absence of
Yes.
fine structure line, which is your strongest argument.
Yes, that is true, but then in the Lyman alpha force, it's very difficult to make this argument very cohesively. And yes, because we had to go into the forbidden forest to do all that. So let me just mention two things that you said. First is there is very careful modeling here, and the model for sulfur 4 and phosphorus 5 come from the exact same parameters, so that strengthened it a lot. The second thing, we now have 12 objects that we have found distances for, and all of them are considerably above a parsec. We have few in the tens of parsecs, few in the hundreds of parsecs, and few in thousands. These results are corroborated from Sept galaxies outflows analysis, both done by us, but more so by the Kremer and Crenshaw group that now have 20 results, all of them putting every single Sept galaxy outflow above 5-10 parsecs, and sometimes in the 100 and 1,000 parsecs. The empirical situation is simply changing, and it is up to you guys to change your opinion about that. You know?